Okay, so let me start with where we were last time. Okay, so we saw the definition of a Cauchy sequence. So I'll just repeat it here since we're going to use it today. So xn is Cauchy if for any epsilon greater than 0, there was some n in the naturals depending on epsilon, so that if you looked at any two terms of the sequence that were far enough apart or far enough down in the sequence, we had that xn minus xm was less than epsilon. Okay? And then the main theorem that we showed was that a sequence was convergent if and only if it was Cauchy. So convergent if and only if Cauchy. Okay? And I guess I showed one way and then the other way is on the homework. Okay? So let me give you now kind of the best application of this. There's a lot of applications of this idea. I'm not sure if this one is actually the best, but we get to see it immediately, and it's quite useful. Okay? So let me give another definition. All right, so a sequence xn is contracting if there's some number between 0 and 1 so that the difference between two terms of the sequence, so I'm starting at xn, I guess. I'm looking at xn plus 2 minus xn plus 1 is less than or equal to c times xn plus 1 minus xn. Okay? So in other words, it's a sequence where the steps, so i.e. the difference between the two terms are getting smaller and smaller. Okay, so since c is some number that's less than 1, so if I know, for example, if I'm looking at, x1, x2, x3, and so on, I can take, x1 minus x2 is some real number, right? Let's just say this is d or something. Then x2, so this is positive. I know that x2 minus x3 has to be less than or equal to c times d, okay, which is in particular less than d. And then this continues, right? So x3 minus x4 is less than c times d, so c squared d, and etc. Okay? So you know that there's this kind of definite amount of decrease between the terms. So like a non-example would be something like 1 minus 1, 1 minus 1, etc. Here the distance between the consecutive terms is staying constant. Okay? So is not contracting. All right, so here's the theorem. Now again, remember, we're interested in taking limits of sequences. There's nothing in this definition which, tells you that the sequence has to converge, and in particular, it doesn't tell you that it converges to some number, okay? So the theorem is that every contracting sequence is Cauchy, and therefore it's convergent, and thus convergent. Okay, so this is another good example. I mean, you can think we're kind of interested in sequences that we know converge without having to work out what the limit was. So we saw, a monotone bounded sequence is convergent. That was able to then show Bolzano-Weierstrass theorem, where we had any sequence has a convergent subsequence. Now we get something where it doesn't have to be monotone, right? These xn's can still hop around a bit, but we know that the gap between them has to be getting smaller, okay? And we still get convergence. All right, so let me prove this, okay? So the idea is to kind of transfer local information, where we know a gap between xn and xn plus 1 into global information. Right? We want to show a sequence is Cauchy. So we need to work out, xn minus xm for all n and m. Right? So knowing something about the consecutive terms plus contraction will help us work out the distance between all the terms. Okay? So let me just first write out more explicitly what we know about the distance between consecutive terms later on in the sequence. So we know for any n, if I look at xn plus 2 minus xn minus 1, this is less than c times xn plus 1 minus xn. And this is less than c times c, xn minus 1, etc. Okay? So in other words, we get that xn plus 2 minus xn plus 1 is less than or equal to c to the n x2 minus x1. Okay, so the gap between the first two terms gives you a bound between the nth terms where you get to multiply by c to the n. And you should think this is actually, this c to the n is getting small very quickly, right? So if c is, for example, a half, then, the distance between the nth terms is like 1 over 2 to the n, or less than or equal to 1 over 2 to the n times the distance between the first terms. And this is, some exponential function, which is shrinking quite fast. Okay? All right, so this is the consecutive terms, and now what you want to do is bound the, non-consecutive terms, right? So now we're looking at something like xn minus xm, and let's just assume that n is bigger than or equal to m. Right? All right, so now we do basically a bunch of triangle inequalities, right? We're trying to get from xn to xm, and the way that we do that is hopping between all of the xn minus 1s all the way through till m. Okay, so this is xn minus 1 plus xn minus 1 minus xn minus 2 plus xn minus 2 plus, this goes on until we get xm minus 1 minus xm. Okay, so I'm just taking these terms and adding all of the consecutive terms in there. All right, and now by kind of repeated application of triangle inequality, we get xn minus xn minus 1 plus xn minus 1 minus xn minus 2, and so on, all the way to xm minus 1 minus xm. And now, what you notice is that we have bounds for each of these by contraction. Okay, so since we know the sequence is contracting, we can put all of these in terms of something involving c and x2 minus x1. So in particular, this is less than or equal to c to the n minus 2 plus c to the n minus 3 all the way down to c to the m minus 1 times x2 minus x1. Okay? Okay, this is just because, every single term I can compare to x2 minus x1. And so I get something which looks very much like a geometric series for c. Okay, so in particular, this is less than or equal to c. I'm just going to pull out an m minus 1, and then you get c n minus m minus 1 plus c n minus m minus 2 all the way to plus c squared plus c1 times x2 minus x1. Okay, so I'm just going to kind of leave it up to you that the that the subscripts are right. You should think this c to the m minus 1 just comes from the fact that we're starting at x sub m, and this remaining part is just the gap between n and m. Okay? So now, this is less than or equal to c to the m minus 1, and this is 1 minus c to the n minus m divided by 1 minus c times x2 minus x1. Okay, so maybe I'll just write this out a little more explicitly, or maybe just aside, right? Remember, did not mean for that to overlap. Okay, so recall that if I look at 1 plus x squared plus x to the n, and then I multiply this by 1 minus x, I get precisely 1 minus x to the n plus 1, right? Because every other term in this, when we distribute, cancels out. Okay? So in particular, 1 plus x to the n is equal to 1 minus x to the n plus 1 over 1 minus c. And therefore, and this is exactly what you get here with these numbers. All right? So now, let's bound this again. All right, so going back to here, this is less than or equal to c to the m minus 1 times 1 over 1 minus c times x2 minus x1. Okay, so this is just because, well, c is less than 1, so I can drop this c to the m minus 1 term out. All right, and now let's see what's going on. Well, this is just some constant, right? As is this. Okay? On the other hand, c to the m minus 1 is going to 0. Okay, so if I take c between 0 and 1 and I look at the limit as m goes to infinity of c to the m minus 1, I'm getting 0. Which means I can shrink this as small as I want. Okay? So in particular, I can make, for large m, I can make c to the m minus 1 less than epsilon times, I just cancel everything out, times 1 minus c times 1 over x2 minus x1. And this calculation now, for choosing this m, shows that I get xn minus xm is less than epsilon. All right, so that's the proof. That shows it's Cauchy. Okay, so I know that's a lot of subscripts to kind of keep track of, but the main point is that you should think the terms are shrinking so quickly that you can, that you can bound anything between n and m by just knowing the distance between consecutive terms. So really the key fact is that the geometric series ends up converging. Okay. All right, let me go here. Okay, so let me mention just a corollary, which I think I'm going to put on the homework. Okay. It's a good exercise to kind of see if you understand this proof. So notice now what this means is that if xn is a sequence which is contracting, well, then in particular we have xn, converges, so we know this goes to x. But actually we know that it converges very quickly, okay? So in particular, if we take xn minus x, so you're interested now in just, how close is the nth term of the sequence to the actual limit? Well, it turns out to be less than or equal to c to the n minus 1 over 1 minus c times the distance between the first two terms. Okay? Similarly, if I have this distance, it's the same as saying c over 1 minus c times xn minus xn minus 1. Okay? So once you know kind of where you're starting, okay? Okay, so maybe the distance between the first two terms of your sequence is 1. Okay, maybe it's like, if that was equal to 1, then you know that if you go out n steps, whatever the limit is, you still, that might be hard to find, but you have a very good approximation of it, right? So go out like 10 steps, and you're something like, c to the 9th over 1 minus c. And for small c, this is quite a tiny number, so you get very good approximation without having to go too far in your sequence. Okay, so let me give you a practical example of this. Okay? So I'll give you a very specific example, actually. Okay, so let's just consider a cubic polynomial. So I'll do like x cubed minus 7x plus 2 is 0. And suppose it has a root between 0 and 1. Okay? So, you could do this in, maybe you just sketch the curve and you notice, oh, it looks like that happens, okay? Or between 0 and 1, maybe you notice that, plugging in 0, so f of 0 is 2, and f of 1 is minus 4. Okay, if you know the intermediate value theorem, this is telling you at some point between 0 and 1, since this is positive and that's negative, you have to hit 0 at some point. Okay? Still, you know that there's a root, but finding a solution might be tricky. Okay? So what we want is an approximate solution. In the case of cubics, there's actually, a formula, a very complicated formula, which lets you find the exact solution. But, that's not usually what people want to do, right? You want to find an approximate solution in a very fast time. Okay, so here's the idea. All right, so let's just take x1 to be some random number between 0 and 1. I have no idea what it is, okay? And that's the point. If I kind of want an algorithm to find a root, I don't want to have to be clever to choose a starting value. All right? So what I want to do is cook up a sequence from this polynomial, so that the limit is the root. Okay? So one way you can do this is, well, you solve for x, which seems a little weird to do in this equation, but you just say, well, x is equal to x cubed plus 2 divided by 7, and then make the sequence, which is xn plus 1, is defined to be xn cubed plus 2 over 7. All right, so it's, again, an inductively defined sequence, and we know that if this sequence converges, then, well, the limit satisfies this equation. And therefore, the limit is the root. Okay? So we found, I mean, at this point we haven't done anything really. We just said instead of finding the root of a function, we're going to find the limit of a sequence. Okay? But now we claim that this is easier to do. Okay? Or at least to approximate. So remember, we started with some random number between 0 and 1. But I claim this implies that actually every term of the sequence is less than 1. Okay, I won't do this out. This is an induction proof. It's similar to one of the problems on your midterm. Okay, but you just, if you assume, all you need to assume is that, well, if this number is between 0 and 1, then so is this number. Okay, and that's not hard to show. All right, so what do we have now? We want to show that this sequence is contracting. Okay, so we take two consecutive terms, and now we write it out. Well, this is, 1/7 times xn plus 1 cubed plus 2 minus 1/7 xn cubed plus 2, which is 1/7 times xn plus 1 cubed minus xn cubed. Okay, so this is good, right? We've already gotten our sequence in terms of something which is a difference of, of the terms in the sequence that came earlier. Okay, so we want to bound this in terms of just xn plus 1 minus xn. Right? That will show that if we can do that, we can show our sequence is contracting. So I'm not going to try to be too clever in the bound, okay? But you do need to know one little factoring trick. Okay, so this is just a statement: x minus y cubed is x squared plus xy plus y squared times x minus y. Okay? Putting this in terms here, we get xn plus 1 squared plus xn plus 1 xn plus xn squared is xn plus 1 minus xn. All right? And this is exactly what we want. And this, on the other hand, is, well, this is less than 1. Okay, I mean, this is at least what I know. This is less than 1. And this is less than 1. Okay, since everything is less than 1. So therefore, we get this is less than or equal to 3/7 times xn plus 1 minus xn. So therefore, we get contracting. Therefore, we know it's converging. And of course, once it's converging, you get that it's converging towards the root by our setup. Okay? So technically I mean, you need to be a little careful here because there might be multiple roots between 0 and 1. In this case, you can pretty easily show that there can't be. In general, that's something that you have to worry about, though, that if you're trying to find one solution, this algorithm might produce for you the other solution. All right. Okay, so let me bring this up now. Okay, so now, what have we gained? I mean, we found a sequence. We know it converges. We wanted to get something from this, though, right? And the claim is that this above corollary gives error bounds. Okay? So let's just, again, we choose this random, choose x1 in 0, 1. I'll just choose a half. Okay, so x1 is a half. And now, you just compute, x2, x3, etc. by hand. Okay, so this seems, somewhat of a pain, but of course this isn't that hard to do, right? A computer could do this essentially instantaneously, right? So, I mean, I'm not a computer, but I can plug into a calculator. So I'll just write out what we have. Okay, what are like the first couple terms of the sequence? So x2 is 0.30357. x3 is 0.2897711. x4 was, okay, maybe I'll go out one more. So again, we want to compute this up to, let's say, x5, okay? So this is 0.28916 9, and so on. Okay? And now how accurate is this? Right? These numbers seem to be getting quite close together, right? Which is what we should expect from contracting. But let's work out exactly, how close we get to the solution by just going out 5 terms. Okay? Well, we plug into the corollary. We know that this root, so xn minus the root, is less than or equal to c to the n minus 1 over 1 minus c times x2 minus x1. Well, x2 minus x1, I'm just going to, you can compute this. I know this is less than 0.2. I'm just being sloppy here. Okay? So I get this is less than or equal to 3/7 to the n minus 1 over 4/7 times 0.2. Okay, so this is less than or equal to 3 to the n minus 1 over 7 to the n minus 2 times 20. Okay, this is dividing by 5, and so you get 4 times 5. Okay, so therefore, the limit, so x5 minus the root, is less than or equal to 3 to the 4th over 7 cubed minus 20, which is 81 over 6860, which is less than 0.012. Okay, so pretty good. Okay, I mean, if we didn't have to go you only got to go 5 terms out, and you got within 100th essentially of the root that you were interested in. In fact, okay, so if you go out one more step, so you want to look at like x6 minus x to the 5th, this turns out to be less than 0.0000005. Okay, so this is tiny. And you get that x to the 6 minus r is less than 3/7 over 1 minus 3/7 times x to the 6 minus x to the 5th. So you get 3/4 of this. Okay, which is less than 0.00005. 0, 0, 0, 0, 4. Okay, so using like the second part of the corollary and going out the right number of steps gives you that if I do x6, which I didn't work out, but it's essentially, well, it's very close to x5, has the same, 5 decimal places as r. Okay, so I want to end just by giving you kind of a general idea of when this works. Okay. So when does this work? Okay, so notice we were starting with x cubed minus 7x plus 2 is 0. But actually what we actually were interested in was finding x which satisfied this equation. Right? Or in other words, if we looked at the function f of x is 1/7 times x cubed plus 2, and then we were looking at f of x is x, we would have a similar picture here where we were trying to, well, a similar picture to what I've drew in an earlier lecture, which I'm not good at drawing. It looks something like this. Okay, sorry, I should have maybe graphed that out beforehand. All right, this is like at 2/7. Anyway, in any case, you'll get something which looks like this, and you want to know when is the sequence, x1, f of x1, f of x1 contracting. Right? So we did this by hand, right? And we, computed the distance between two different values, but you'd like a general formula so that you can, apply the above ideas, know that it converges, and be able to quickly approximate solutions. Okay? So the condition, which I'll just, haven't even said what a derivative is yet, but maybe it won't be too surprising, that the condition is that f of x gives a contracting sequence on an interval AB exactly when the first derivative of x is 0. Oops, sorry, not is 0, but is less than 1. I should put that here. For all x in AB. Okay, so in other words, you want your function to have slope smaller than the function y equals x. Okay, so notice here for our example we had like f prime of x is just 1/7 times 3x squared, and this is less than 3/7. And it's no surprise that this was, well, it turns out that it shouldn't be too much of a surprise that this 3/7 bound is exactly what you get from the derivative when you have x between 0 and 1. Okay, so in fact, you can show that if f prime of x is equal to lambda less than 1, then you get some lambda contracting sequence. Okay, so lambda is the c between 0 and 1 that you use. And it turns out in this case, there is a unique fixed point where f of x is equal to x. Okay, so there's a unique point here. Now I know that I drew another point here, okay, but you can check the derivative at this point and it's greater than 0. Okay, so this other intersection point is, is less than, is greater than 1. Okay, so you don't notice it if you stay in the interval 0, 1. Okay, so in this case there's a unique fixed point, and if I take like some x1 in this interval, and I look at x1, f of x1, f of x2, this converges to this x, and very quickly, okay, kind of exponentially quickly. Okay, so I thought maybe I'll just leave as an exercise, like one more kind of example here. Okay, so we're going to approximate the square root of 3. Okay, so I'll give you a function, all right, which is f of x is a half x plus 3 over x. Okay, so you can check that if x is equal to plus or minus square root of 3, we get that f of x is equal to x. Okay, so I want you to show, and this is just an exercise, as I said, show f is contracting on an interval. Okay, choose an x1, compute, say, x6, and compare to the calculator's value. For square root of 3. Okay? Just to see how kind of close you get. And you, of course, should choose an x1 which is reasonably close. Okay, if you choose x1 to be a trillion, then, it will take longer. Okay? But if you know the square root of 3 is, say, between 1 and 2, okay, then that should give you a good hint as to what you should first check. Okay, so I'll stop there. Thank you.